Hello guys, you can hear me well?
Yeah,
You can see my screen as well?
yeah.
Yeah.
Okay, so today we're gonna explore or learn bits first search, but how to code it in C++. Okay, based on that you will have homework to modify the code to implement depth first search. I just give you some hints about that code. Okay. Then after returning the assignment, I will after 1 week I will publish another 2 assignments, which is implementing like extras and A star based again on the same code. Okay, again it will be little changes. Okay, so let's start by a simple example. Okay, about what we're gonna do. Breadth first search. We will not do many stuff this lecture. I will just let me just open the slide here. Yes, I will just do a simple example which you can see on my screen right now in the tablet. Then we're gonna explore coding that I did in C++. Okay, so unlike MATLAB, okay, coding in C++, dealing with array is much different. Okay, for example, the rows in C++, the rows in C++ starts by 0. So here, this row 0, row 1, row 2, row 3. And the same for columns as well. So 0, 1, 2, 3. So for example, the coordinate of this cell is 0 and 0. The coordinate of this cell is 0 and 1 because it's in row 0 and row 1 and so on and so forth. Okay? So based on that, the IDs will be, by 1 but back. So instead of from 1, I'll start from 0. So the 0 of the cell is 0, 1, 2, 3, and so on and so forth. So here, this will not be 16, it will be 15. In MATLAB, it will be 16 because we start from 1. But here we start from 0, so the ID will be 15. And unlike MATLAB as well, we're gonna do the coding to figure out the ID or the index ourselves. Okay, we're gonna write the real equations, not like MATLAB, subscript to indices or indices to subscript to convert back. No, we're gonna do that ourselves. Okay. Unlike MATLAB, also we can use queues. Okay, and you remember in breadth first search, we need FIFO. Okay, luckily C++ has some library that you support such kind of data structure, which is Q or FIFO. Okay, and basically everything else is the same, except that we are, we have to do many stuff ourselves. Not like MATLAB, because MATLAB, is very nice and easy. Everything has a function out there. Okay, but here no. Many things we have to support ourselves, as we will see. But the same concept. Maybe the only thing that C++ afforded to us to make the operation of the coding is simpler is the queue data structure. Other than that, of course, MATLAB is easier. Okay, so I'm gonna do this simple example with you. Then I will explore the coding, the C++ coding. So here we have a simple example. We have 4x4 map. We have the start node here, the goal node here. We have also some obstacles, but I can't remember exactly where is the location. So let me grab them quick from here. Guys, just give me 2 minutes. I will get this phone and get back to you. Okay, I will just mute a moment. Hello, guys. Sorry for that. Okay. So let's go back. Okay, so let me get the obstacles for you here in that example, the location of the obstacles. So we have one here. So this is an obstacle cell. and one here. And two others here and here. Not much complicated, okay, but it will give us a very good idea about how the coding will look like, okay? So we have a queue, a FIFO queue, that we're gonna, fill and add and remove from, okay? So in the beginning, we're gonna add the starting node, which is node 12. We have only that one here, okay? Then we're gonna explore. We have only one neighbor, which is 13. So we're gonna add this. So erase. I'm gonna add the new one, 13. Okay, and that's it for the start node. No other node can be explored because this one is obstacle. This is out of the map as well. Okay, so we have only two nodes right now, and we finish exploring, okay, the start node. So we're gonna make another array first, which is the parent array, and this parent array, for example, we have 16 places here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And initially, everyone here has a -1, means, or infinity like in MATLAB, okay? But there is no infinite here in C++. So we're gonna fill it with infinity. I'm sorry, with -1s. -1 means it's not explored. The cell is not explored, so it has no parent. And now we explore node 13. So we're gonna, and the parent is 12, which is a start node. So we're gonna change this entry here to 12. Good. And then, since we end exploring node 13, we're gonna remove it from the queue. So we're gonna let's remove by just making some. This means it's removed from the queue. Then, so we have explored this guy and this guy. So let's call this the exploration step, for example, which is 1. Then we need a new frontier. So we look at the queue, and we just take the first 10 will be first out. We have only, so this is away now. We have 13. So this will be our next frontier. Then we explore around. Okay, we have up, it's visited before. Okay, the right is out of the map. Left is not visited before. So 2 means exploration step number 2. And we're gonna add it here, 9. And we change the parent of 9, which to be 13. So this will be 13. 9 will be 13. Down is also explored, so 3. And we're gonna change the parent of 14, which is this node here, to also 13. 14 will be 13. Good. And we add it to the queue as well. Now we finish exploring 13, we remove it from the queue. Just remove it. So the queue now has 2 elements, 9 and 14 only. Now we need a new frontier. So this was the previous one. We will do this. First in, first out. Okay, so 9 now will be our new frontier. This is a wall, cannot be explored. This is visited before, so cannot be explored again. This is obstacle. We have only 10 here. So this is step number 4, and we're gonna add it here. This is node 10. And we change the parent of 10 to 9. Good. Since we finish exploring 9, we just remove it from the queue. Bob. Okay. We need now a new frontier. So this guy here, 14. So this is visited before, out of the wall, visited before, we have only 15 here. So this is step 5, and this is 15. And the parent is of 15 is 14. The current frontier. We finished exploring 14, we removed from the queue. Bob it. A new frontier will be 10. Now 10 has, 2 explored before nodes, so visited before or explored before, we will not touch them. Then we take 6 and 11. So if we have a priority of up, right, left, down. So up is explored, right is explored before, then we go to left first, so we're gonna add 6 first. And it's the parent of 6. It is 6. It will be 4. It will be 10. And then we got, so this is step number 5. Then in step 6, we're gonna add 11 and change its parent as well. So 11 here, the parent will be 10. And that's it for 10. We finished exploring it. So remove it from the queue, Bob it. Of course, when we put a new element in the queue, we push. When we take something, eliminate it, Bob. Now we need a new frontier, will be 15. This is 15. So out of the queue, out of the map, and this guy here is explored before, this guy here is explored before. We finish exploring it without adding any new item. So we just, remove it. Move it. New frontier would be 6. Explored before, out of the map. So we're gonna add 7 only. And it changes the parent of 7 to 6. Oh, I'm sorry. This one here, 7, it's 11. I'm sorry. This is step number 6. The ID is 11. Okay. So this node here, 11, discovered node 7. And this exploration step is also 7, by chance, by accident. We need a new frontier, which is 11 here. 11, its neighbors, 3 of its neighbors, this guy and this guy and this guy, as explored before. And this is out of the map, so we just, remove it. So we remove 6 first. Then we remove this 11. And now we have only one frontier left, which is 7. And 7 again, this guy is explored, this guy is explored out of the map. We're gonna add only node 3, which is the goal. Then we're gonna bob 7, choose a new frontier, which is node 3 or the goal. So we're gonna end our exploration. So node 3 has a parent, which is 7. So we're gonna change it as well. Now let's trace back the shortest path. Just explore the parents. So this is the goal here. So the goal has a parent which is 7. So let's do that in another color. This color, for example. So, and 7 has a parent which is 11. That one here. And 11 has a parent which is 10. That one here. And 10 has a parent which is 9. This one. And 9 has a parent which is 13. And 13 has a parent which is 12 for the start node. And of course, the start node has no other bits. The first one here. So we construct the shortest path. Okay. So basically, the good thing about C++ programming is that, you know, it has priority queues. So you can use any of them based on your problem. Okay. So now, anything not clear here, guys? Anything need more exploration or explanation? Okay.
Mr. Mustafa,
Yes, Johnny.
is the steps wrong for 6 and 11? Because you have 5 twice.
6 should be 6 as well. 6 steps, same as 11.
Oh.
So it'd be
But
6,
why?
7, and 8.
No, guys. We discovered node 6 first before node 11. So it's up. So, okay. The parent is 10, right? Right or wrong?
That's right.
6 and 11. Yes, the parent is the same, which is 10. So this node, this frontier discovered this node and this node as well. Okay? When we explore this node, when we explore these two nodes, we have this priority up, right, left, and down. Okay? So left is before down. So
I think you mean because node 15 has 5 as well on the steps.
Ah.
Yeah.
Okay. Yeah. Now yeah, I messed up with the step, but doesn't. Okay. Let us do it again. So very quick. 1, 2, 3, 4, and then from 4 we discovered the 5 and 6. No. From 3, we discover 4 and 5. That's right. Then 4, we discover, okay, this and this. So this will be 6. You are right, guys. And 7. Then this will discover this will be 8. Okay? I think now. So 0, this will discover this. And this will discover these two. So 2, 3. This will discover these two as well. So 4 and 5. This will discover these two as well. So 6 and 7. And this will either this or this, that's fine. Will discover this guy. So this will be 8, and this will be discover the goal. Okay or not?
It's good now.
Okay. This is exploration steps. Okay, which is a metric for time. The time consumed. Okay, something similar to time. But the shortest path is the same still. Okay, it doesn't interact with such a glitch in the steps needed. Okay, in each exploration step. So let's now do the coding. You need to understand this coding very well because you take it as a structure to do depth first search and Dijkstra's and A star. All will be based on the same coding here. Okay, it has a little bit of complexity because of some inflexibility in C++. Of course, MATLAB is a very high level programming language. C++ is about to be low programming language, low level programming language. It's closer to assembly than MATLAB, of course. Okay, so let us see here what we have. Okay, so we have some libraries that we need to include. Okay, so we can use some features, and so I will explain which one is used for which. Okay. Okay, so for example, IOStream here is needed for the cout when we get something on the screen as output. Okay.
Professor, are you sharing a different screen now?
Yeah, I forgot to do that. It's really confusing to
It's okay.
to share a lot of screens.
It's totally understandable.
You can see my coding?
No.
No, so
Oh, no, yeah.
Yeah.
Yeah, we can now.
Okay, good. Okay. So we have here some libraries. Okay. So IOStream is for cout. This is the queue is for the queues, the FIFO queue. Array is for array. Map here is not a map that we're gonna draw. So this is something very different. Okay. Map here is actually a dictionary. It's another type of data structure that we will need further in this coding. You guys have any idea about this dictionary in definition in C++?
I do not.
Okay, when we reach it, we're gonna explain back on the tablet, but we're gonna need it. Okay. This conuf.h, we needed to make a break. You remember something called the get character. Okay, if you wanna pause the output on the screen, okay, in the console window, then it will only be continue if you hit the keyboard. We're gonna also reach it, and I will show you how everything is working. I can't remember why we need thread and chrono. We needed to set up some time, some delay. I will show you. Also in the output, it has no relation to breadth first search. It's only for the output stuff. Okay, and this is actually okay. Let me open the other project. I will open. It's actually another project here. Okay. It's exactly the ones that I was showing you is the DFS, the depth first search, which you're gonna do yourself. But this one is, the basic code that I built upon DFS. So it has the same stuff. So again, IOStream is for cout. Sorry about that. Q is for FIFO queue. Array is for array. Map is for dictionary. We're gonna see it in a little bit, and I will explain it to you. So the last three is actually for debugging. The output to the screen. Okay, so let's start this. So this four stuff here is only for outputting. Okay. Output data to the console window. Okay, and we have here some maps, and here is the way that I define maps. Okay, for examples, example 1, example 2, 3, 8 examples. You will have 8 examples. Okay, so before going deeper in the code, let's have a run and see what's gonna happen in the output. So let's say, okay, 1000 millisecond, and let's see what we will have. So this is the map and how it's evolving, okay? So each F means frontier, E means explore the frontier. I know that was a frontier and it's explored and we finish its exploration, okay? And this asterisk means unexplored cell, but not a frontier yet. And once we reach the goal, we construct the path in that way. So we write some text in the map, okay, or the input map. We write some texts that, you know, show us how to navigate from the source to the destination or the goal. So we use this greater than and less than, you know, the exponent hat or the exponent symbol in the keyboard and the letter V, okay, to represent the directions. So for example, from the start, we go to this one, okay? This one means then we'll go to left, then go down, left again, down again, then left until we reach the goal, okay? So let us play with some of the, so let's make a break. So this between each two outputs. And then we're gonna show you why we need to do that. So here I'm setting that I want a break between each two outputs. So let's see what's gonna happen. Let's run again. Okay, so this is step 1, step 0, you can say. So we have here the start node. This is our first frontier, okay? But I will not mark it with F just to make it easier for you to know if each time where is the start and where is the goal. So the start will explore this node first, okay? Because it has no other node to explore. Because this one means, you know, it means a wall. 0 means, you know, unexplored cell. It's a free cell, but it's unexplored. Asterisk means a cell that is free and explored. Okay. Then at step, we're gonna take another frontier, which is the one that we discovered, because S has only one neighbor, valid neighbor. So in the second step, we're gonna pop the start as a frontier, and we will have only one node, the queue, which is this node here, and it will be our current frontier. So let's go one step further. So this node will discover this node for us in the first step, or the third step now. Then it will discover this node. Okay, and finish the exploration of that node. So we will mark it with E, means that was a previous frontier, and we finished its exploration, and now we need another frontier. Okay, so we're gonna look at the nodes that we have in the queue right now. So the nodes that are in the queue right now and can be a candidate to be a frontier is the asterisk nodes. These are cells that are explored but not yet chosen as a frontier. Okay, you have here the notations. So F means the current frontier, E means the previous explored frontier, S means starting node, D is the goal, or you know, I just messed up. So this should be G. So G, because I can sometimes I call it D and sometimes I call it G. Okay. So at that time I was calling it D, that's fine. 1 means obstacle. 0 means a cell that is not explored. It's a free cell but not explored. And asterisk means it's a discovered but not yet play as a frontier, not yet chosen as a frontier. So at that moment, at that step, we finish exploring that node, so we mark it with E, and we need to make another frontier. Okay, it will be one of those. And see, the code chooses this one. This is our current frontier right now. Okay, so it's gonna explore the cell below it. It's the only one. then it will be marked as explored and bob out from the stack. And now we need another frontier. We have two, these two here, these two asterisks. So we're gonna choose one of them. It will be that one because it was pushed into the queue before that asterisk here or before that node. That also has one node to explore, which is the node below it. That's good. Now we have another two nodes in the stack, and we finish exploring this node here, this F here. So we're gonna mark it with E, explore the frontier, and we're gonna choose another frontier, which is this one right now. It will explore two other nodes, the one on the left and the one in below. We finish exploring it, it will turn into E. Explore the frontier means, and we're gonna bob it from the stack. You're gonna see this in the code. We get another frontier, but it has no node to explore. So we just, in the next step, we didn't find any new nodes to add. So we just mark it with E and bob it out of the stack, out of the FIFO, I'm sorry. Another frontier, another node, end of exploration, a new frontier. It will not discover anything because everything is discovered. So it will be marked, bobbed out of the stack, a new frontier. This will discover the goal node. Remember, the goal node is not discovered till this moment. So this will add the new node, then it will be marked with E, end, because it discovered only one node, and that's it. In the next step, we're gonna choose G as a frontier, and since it's the goal, so this is the end, okay, of the while loop. Then we go to another part of the code that determines the shortest path based on the parent ID, and make this cool stuff in the map to mark the route between the source and the destination. Okay, so that's how the code works. If you don't want, of course, these are all for debugging. Okay, but of course it takes time, just like MATLAB. So if you don't need to show all of that, okay, you can choose not to show of that by marking this verbose output false by false. So this variable here, if it's false, the code will not show all these steps for you. Okay, so let's try this. It may show only the last step. Yeah, only the last step. Okay, if you don't want the break, mark this was false between the outputs. So we don't need to hit the keyboard each time. Okay. Because we have false. So let's bring that back as true. So it will show the outputs, but with no break in between. And the time between two outputs is controlled by this variable here, wait period. Okay. It's the time in milliseconds. We will see that in the coding itself. But this is the variable that controls the time between two outputs. And that's it. If you want to list time, you can control that. For example, let's say we want a 100 milliseconds. It's of course very, very small time. It's 0.1 second. You see how the acceleration. You have now output, but it's very fast. Okay. So you can control that using this variable here. Let's save it as 1000 milliseconds, which is 1 second between each output. Now, how to control or how to choose the map, okay? You have some examples, but unfortunately, each example has its own map size, okay? In MATLAB, that's not a problem, okay? You have many examples, you know, just comment and uncomment. It's really headache here, okay, to have many examples and switch between them smoothly. So we need some way, okay, to choose between examples. So I made that that cool stuff here. So I define here a variable, a macro, okay, and based on the definition of the macro, we're gonna choose a map, okay. So you see, you guys can see there is a difference in the contrast of the color between that part and that part, right? Or you can't see the difference?
Yeah, you can.
Good. That difference in the contrast because of the definition. So basically, I am defining one macro here called example one, okay? And I am saying here, if you have a macro called the example one defined, then execute that part of the text. Then I have else if with another macro called the example two, which is not defined. So all the else's here will not be executed. Actually, since this is the compiler itself will only see, you know, this part, okay? So the pre-processing of the code before compilation will only show that part to the compiler, okay? But that's, you know, that's not, if you didn't understand or get it, that's not a problem, because this is only, you know, part of the code that is not breadth first search or depth first search or whatever, okay? That's only, you know, something, you know, we need to add, just to add some example to test our code with. So we didn't reach that breadth first search yet, okay? So if I want to choose example two, what I should do? I should define example two, a macro called the example two, and I should undefine or not define any macro called the example one. So this will be false, and the code will go and, you know, highlight this text for me, and the compiler will only take this one and ignore the rest, this one, and, you know, the one below. So this is very easy step. So just to change this to two here, okay? Look what happened now. Now there is no macro called the example one. So this is not defined. So this is false. If defined the example one, it's false because there is no macro called the example one. So this is false. This condition is false, or this condition is false because there is no macro called the example one. So this part of the text, this part of the text will not be visible, okay? Will not be executed. But we have a macro called the example two. We have a definition called the example two. So this will be defined and executed or compiled, we can say. We don't have a macro called the example three or example four or example five. So all such stuff from here until the end will not be executed. So we have all the time one map to play with, okay, or one example. Okay, what you need to choose between them is just change the macro name. Okay, if you want example 7, just make this 7. Let's do that. So if we save, then, you know, you see now all these, the contrast has of the color become very less, and only example 7 will be highlighted because this is the one that will be executed after when we do the compilation, when we compile that code, because there is a macro called example 7, but there is no macro called example 8 or example 6 or whatever else. Okay, so that's how we choose between these examples. Give yourself, you know, 5 minutes when you study this code, and you will find it easy. It's not hard. If you didn't get it with me now, you can ask a question right now, okay? But even if you didn't understand it at all, just, you know, give yourself 5 minutes when you study the code, and you will find it easy. It's not hard at all, okay? So in example 1, we have a map with 4 by 4 column. We have a map of 6, just like the one that I explained on the tablet. A map of 4 by 4, 4 rows and 4 columns. And here is the map itself. So just a grid, okay? You need not to define both dimensions, although you can do that, but you don't need to, you don't have to. So we can put that here or just remove it. That's fine, that's very fine. It's not an error at all, okay? And you can remove it as well, that's fine. So you can make both. So 1 means an obstacle, 0 means a free cell. S is the start, G is the goal. Okay? That's good. And you'll have the same notation in other examples. For example 2 here, if you are choosing example 2, let's do it very quick. So we have 10 by 10 map, 10 columns and 10 rows. And again, here are the obstacles. Here is the start node, here is the goal node. By the way, these are the same maps that I was doing in MATLAB, but I just put them in a format that is acceptable for C++. That's it. That's the only difference. Okay. So let's do our examples with example 1. It will be much better. Yeah, much easier to explain. Okay. Let's go to the main code, and from the main we branch it, you know, to the functions that we are using. Okay, so this is the main. We need to define, you know, the ID of each cell, especially the ID of the start and the goal nodes. So we define 2 variables, integers, of course. One of them is called the start node ID, the other is called goal node ID. We need also to define our map. Okay. So we will have the example that I showed you, the grid, this array called the grid. I call this array in the example, I call it grid. Okay. But we will copy its values to input array, so we can change whatever we want, but keeping the original the same, without playing with it, without messing up with it. Okay. Any change you want to make, you want to change any entry to F or E, like the examples that I showed you, you play with the input map, not the grid itself. Okay, so just to keep the original grid the same as a reference, we can say. So I create a map, an array called the input map, okay, which have the same size, of course, like the grid or like the example, row size, column size. In that case, when we choose example 1, row size is 4 and column size is also 4. Now we need to copy the grid entries into input map. We need to copy this array here called the grid, which we want to keep the same values all over the example or the execution, into our new created array called the input map. So we're gonna use this one for the memory copy. Okay, so this function here in C++ will copy the entries of grid into this array input map. But you have to enter the size of the grid, okay, by entering the size of grid. Okay, so after this execution of this line here, the grid map will be just copied into the input map array. Okay, exactly, it will be exactly the same. We need also, yeah, this is a dictionary that I was telling you about. Okay, we need a dictionary. Okay, this dictionary has, you know, each entry. I will explain it right now on the tablet. Don't worry. each entry in this dictionary is, you know, ID, or what we call key, and a value. The value will be the parent, and the key is the ID of the cell. So let's do that on the, let's explain more on the tablet, okay, to show you what's exactly this dictionary. So this is actually the dictionary here. You guys can see my tablet, right?
Yes.
Yeah.
Good. So this is actually the dictionary here. Dictionary. You see each entry has two elements, we can say. Each entry, each you know, element has two entries in this data structure. We have a key, this is called the key, and we have a value. The key will be the ID of any cell. So we have cell called 0 here, cell number 1, cell 2, cell 3, cell 4, 5, 6, until 15, which is this one. And you have to have unique keys. So each entry should have its unique key. Okay, and of course the ID of any cell is unique. You can't find any cell equal to 15 rather than this cell. Only this cell can have ID of 15. Okay? And the value will be the parent. Okay? So basically the dictionary, any dictionary here in C++ can be written in that way. So for example, if you have 4 entry dictionary, it will be something like this. Key 1, value 1, key 2, value 2, key 3, value 3, key 4, value 4. So if the keys represent the cell ID and the values represent the parent, if I want to know the parent of any cell, I need to know its ID. So I will write it in that way. Dictionary of key X. This will give me value of X. This means the parent of cell key X, the cell that has ID equal to KX, equal to val X. So val X is the parent of cell key X. So for example, dictionary of key 0 is equal to val 0. Okay, so I will use that, you know, that data structure as, you know, a container for my parents. So for any cell, I will have its parent up there. You can do, of course, you may think, oh, we can do it another way. We can, you know, create any regular array. For example, you can create an array here. This array has 16 rows and 2 columns in that way. Or even, no, just one column, okay? So just 16 rows and just one column. And the value of the first place here is actually the parent, for example, of cell 0. Then parent of cell 1, parent of cell 2, until the parent of cell 15, this one. You can do also in that way. That's very fine. Okay. But dictionary is really cool. You should do, whenever you have unique IDs, you should use the dictionary. Okay. It has very, very good features. If you want to sort, for example, there is, well-defined, sorting algorithm for just one line of code. You can sort it. You can get whatever value from there in one line. So once you have a predefined data structure from C++, then you will have also some predefined functions that you can use just in one line. If you use regular arrays, then you need to make a for loop, and lots of other stuff. But if you use a predefined data structure, then you will find some functions also that that is relating to that data structure that you can use, and this will save coding and time from you. Okay, so let's go back. Any question on the dictionary before I go back to the coding?
Mr. Mustafa,
Yes.
how do you know how many entries are in the dictionary?
Okay.
Because
So
below you had 4.
You have what? Yeah.
Below you had 4.
The example. Okay, this is just an example. Okay. So the real values is actually the size of the map. So the number of values we need equal to the size of the map. So each cell in the map may be explored, and once we explore it, we need to know its parent ID. Okay, so we need to book a location for it or entry for it in the dictionary. Okay, so when you discover any node, you just go to the dictionary and set the parent of this node, the values of that key, of that ID, to whatever parent you have, parent ID. Okay, so here we have in that map, for example, we have 16 cells. Yes, I know that 4 of them are obstacles. They will not be explored, but not to make it complicated, you can just make, the number of entries in the dictionary just equal to the number of cells out there, although 4 of them will not be used at all because they are obstacles and basically they will not be explored and will not have parents. Okay. So, but of course, if we want to avoid that, it will be hard for us. We need to know how many cells that are obstacles, create a for loop. It will be a hassle. Okay, so just create a dictionary with the size equal to the size of the map, the number of rows multiplied by the number of columns, which is equal to the number of the cells in the map. Okay. Any other question?
Just a quick question. You know how in a normal array you access an element just by its position? For the dictionary, would you just have to reference the element by its key?
Yes, it's ID. So for example, for example, if we want to know the ID, let's go back to our example here. Okay. So in that step here, we trace back, right? We trace back from the go to the start, right? And in each step, we need to know the parent. So for example, G is 3. Okay, we need to know the parent of G. So we write it like this. So parent equal to the dictionary of the key. What is the ID of G or the go is 3. This will give us 7. Okay.
Yeah.
Then we need the parent of 7 again. So dictionary of 7. This will give us 11. Then dictionary of 11. This will give you 10. Then dictionary of 10, 9, 13 until you go to the start node. Okay. Clear or not?
Yeah. That's just a question I have.
Any other question, guys? Okay, so let's keep going here. Okay, so this is the parent. I'm sorry, this is the dictionary. So our dictionary here called parent. You can name it whatever. I'm sorry, I didn't share the screen. I'm very sorry. Okay. Yeah. Okay. So our dictionary here is called parent. Okay. And to define a dictionary in C++, we use this map. Okay, this is different from our map that we are dealing with. Okay, the input map. No, this is to define a dictionary in C++. And as I said, each element or entry in the dictionary has a key and a value. So you must define the type of the key and the type of the value. In our example here, the type of the key is integer and the type of the value is also integer. Okay. It can be, by the way, based on the application. But in our application, it's integer and integer. This key can be, for example, name. Okay, for example, name and age. So this dictionary can be, for example, the key can be names. For example, you have a class and each student has a certain age. Okay, so if you want to know the age of each student, you call this dictionary by the name of the student, which will be string, and the value will be integer, or the age of the student. So in that case, for example, I want to know the age of student called Mark, whatever. So I will say age. Let's call the dictionary age. So age of Mark, and the Mark is a string. The key here is a string, and C++ will just go and look for this key called Mark, and it will give me its value or its age in that example. Okay. Okay. So our dictionary here is called parent. Okay. And okay, here I'm initializing this parent. Okay, so I create a function called initialize parent, and I send here the size, okay, of the number of elements in that, because when you define a dictionary here, okay, you don't define a size for it. You can do that, but I found it simpler to do it in that way, to define it without size. Then you send the size separately to some function, so that you can make a for loop there and go to each element and you just initialize it with -1, just like what we have done in the example. In the beginning, we mark all the parents with -1, means this cell is not explored, so it doesn't have a parent. Okay. How to know the size of the parent? There are two ways. You can just here multiply, row size by column size. Okay, let's do it in that way. That's much better than this. So row size multiplied by column size. And you can do it also in the way that I just removed. Maybe it will be confused. It will make some confusion for you. So let's keep it in that way. You can do both, okay? But anyway, that's much simpler. Row size multiplied by the column size will give you 16, and we have 16 elements, okay? Or 16 cells in the array. That's good. So let's go to this function here, initialize parents. Okay. So here you receive the size, okay, map size, and you receive also the dictionary. Okay, and here you send it by reference. Guys, call by reference and call by value or not? If you don't know, just let me know. Guys, the call by reference and the call by value or not?
I do not.
You don't know, you, okay.
Yeah, I don't know. Wow.
Okay, so basically you can send an array, for example, or a variable, let's call it a variable, to some function, okay, just by its value. And in that case, if you change the value there in the function, it will not affect the original variable in the code that calls this function. Okay? If you send a variable by reference, like what we have in here, so if I make a change for parent in that array here, it will be reflected back in the original definition of parent, okay, in the code. So basically, this parent is the same as the parent in here. The ones that we defined here, because I'm sending its reference to the function. Okay, that way, when I change parent in the function, it will be reflected in the code here. So this is just another copy of this guy. Okay. If I remove this ampersand here, it will be called by value. And if I did this, when I change or initialize this parent here, this will not affect, shouldn't affect the one in the main function. So I have to do that, okay, to reflect the change. And here I make a for loop. So in our example, we have a 16 cells. So I will loop from 0 to 15. And in each time, I will update each entry, okay? So I have the IDs of any cell from 0 to 15, okay? And in each time, I will update just one entry at a time in each iteration. So for example, in the first iteration, I will update the parent of cell 0 by -1. Second iteration, I will update the cell 1 with again parent of -1, okay, and so on until I reach 15. The last cell is 15 in a 4x4 map, okay. So that way we initialized the parent array. Good. So that's this one here. So yeah, then we go to the main function. I'm not the main function. Yeah, the fundamental, functions that will make the BFS exploration. Okay, which I call, it's a function. It's a C++ function called BFS, Breadth First Search. Okay. This function Breadth First will do the Breadth First Search algorithm for us. It takes the input map as input. It takes the parent. Okay. It takes also the start node ID and the goal node ID. Okay. So let's go there to this function BFS and see. Let's see what's happening in there. Yeah, it's in here. So this is it's a very, very big function. Actually, this is the fundamental part of the code of the file. Okay. Okay. So I made here a class or a structure called the queue item. This one here. Okay. So this is basically a very normal C++ class. Okay. So when you define a class, you define basically a new data type. Okay. So this can be visualized as a new data type, something like integer. Okay. So this data type has 4 entries. So when I define a variable of the type queue item, and I will explain in a moment why I call it queue item, we basically define 4 different variables at the same time. It's something like a person that is known for 4 things, for example, his weight and his length, his name, and his, for example, whatever, eye color, for example, okay? Something like this. Or a student with 4 grades, his grade in course 1, course 2, course 3, course 4. So if I define a student with such kind of data type, it will have 4, characteristics, we can say, or will be defined with 4 different values. In our map here, we define each cell using its row, its column, its ID, and its distance from the start, or from the start. Okay. And in Brett's first search with uniform maps, this distance or this dist here variable will define the minimum distance of that node to the stop. So any node here in the map will be defined with 4 variables, 4 characteristics. Its row, its a column, of course, because it has a coordinate in the system, in the map. It has ID, and it has, distance from the start. It's distance from the start. And this is the way we define it. So we make, how can I say, a struct, okay? Because, classes in C++ just like structures, okay? And this class has 4 entries or 4 characteristics or 4 variables. This will define any data type that I define with Q item. Okay. Good. So, for example, for a start node, in our example, it has a column of 3, row 0. Its ID is 3. And its distance from the start is just 0 because it's the same start node. Okay. That's good. So I define here a variable called start, which is actually start node, but I don't know anything about it yet. I know there is a start node in the map, but I don't know where exactly it is. I know the grid. Here is the grid. And I will explore this grid to know where is the start and the goal nodes. Okay. You remember, guys, in MATLAB, okay, we made any neighbor we explore, we need to know if it's within the map or not, if it's obstacle or not, if it's visited before or not, okay? And if you remember, we make these checks, and if it was visited before, we just skip it and take another neighbor to explore, and so on and so forth. If it was obstacle, we also, make continue and go to explore another neighbor and so on. So we create here an array called visited, because when we explore a node from some frontier, then we don't need to visit it again. So we need to mark it as visited somehow. So we create an array called visited. It has exactly the same dimensions as our input map. And if the entry of any cell there is false, that means it's not visited before. So we can explore it. If it's true, then it's visited by another frontier, and I shouldn't explore it again. Okay. Good. So what we're gonna do, since the obstacles are are not explored the cells because they are basically obstacles, if we mark them as visited, we basically will not visit them, okay? Because they are visited. Also, yes, they are virtually visited, okay? So what we're gonna do here to avoid making this a check if it's a barrier or not, although we can do that, we can, to save this step, we can mark any obstacle as visited node, like if it was explored before, although of course it's not. Okay, but the main objective here is to avoid, adding extra checks that if this cell is an obstacle or not. Okay, so to save that a check, we can mark the obstacle cells as visited. or making them true in that array here. Okay, so we're gonna loop over the array from 0 to row size, and from 0 column to column size. We need two variables for that. And for each cell, if the corresponding grid cell is 1, that means it's a barrier, then we mark the corresponding element in visited as true. Okay. If we discover the start node, which has a letter S out there, then we mark its row, its column, and its ID, okay? And we put it in this start variable here. This start variable of the type Q item. It's an object from Q item. So it has 4 entries: row, column, ID, and distance. And of course, the distance of the start node to the start node is just 0. So we just only change the first 3 entries here: the row, start.row, start.column, and start.id. And to calculate the ID of each cell in C++, we apply such neat equation here. The ID is equal to the row number plus the row size multiplied by the column number of any cell. Okay, here is the general equation. The ID of any cell is equal to the row index plus the row size multiplied by the column index of any cell. Good. Remember also, we don't know the exact location of the goal. We know that the map has a certain cell called G, but we don't know where exactly. So we have here a cell called G, but we don't know where exactly. So we're gonna search in the same loop that we mark barriers as visited. In the same loop, when we find while we are looping, when we find the goal, we can determine its ID as well. Okay, they're using that coding here. Good. Now let's apply the breadth first search algorithm. Okay. We're gonna create a queue, the queue that I was discussing with you. Okay. But the ID, the entry, each entry in that queue is of type Q item. That's why we call it Q item. Any item in the queue is of type Q item. Okay, that's why. So any entry in the queue has 4 features, 4 characteristics. It's a row, it's a column, it's ID, it's a distance from the start. Okay. Then we push the first point. We have the first node, which is the start in that queue. And remember, start we define here as a queue item, so it has the same type as the types of the entries of the queue, which is queue item, and it has 4 entries: I, J, and ID, and distance for the start, of course, is 0. Then we mark it as true. So visited of the start.row and start.column is equal to true. So whenever we have a frontier that is beside or neighbor to the start node, it will not visit the start node because it's already visited in the first iteration. Now we go to the queue. I'm sorry, to the infinite while loop. Okay. that we will only exit if there is no queues, if there is no elements in the queue, or when we discover the goal node. So these are the two conditions that we break our while loop because of. If we discover the goal, like here, or you didn't discover the goal and there is no other frontiers to explore, the queue is empty. That means you could explore whatever you can reach from the start, but you couldn't reach the goal node, so you cannot reach the goal node, and there is no route between the start and the goal. Okay. In each iteration, we need the head of the queue. The head of the queue. Okay. So for example, in the first iteration, we have only one item in the queue, which is a start node. So we're gonna just pick it up. Then we're gonna remove it from the queue. But don't worry, because we're gonna add later when we explore the neighbor cells. Good. We're gonna make our check if this is the goal node or not. If it is the goal node, then we're gonna break. And the break here is actually just return the distance from the start. Okay. So whenever we got a finite distance, some value, okay, other than -1, as we will see later, then there is a route, and here is the minimum number of hops or the cells between the start and the goal node. Okay. So that's basically how we're gonna break the loop. We don't break actually. It's only we return, we exit the whole function. Okay. So now our frontier is in B. We checked if it's a goal or not. In our example, the first entry is the start, it's not the goal. So this will not be hold, so we're gonna go here. This is just to show the current frontier. So if you set this verbose output as true, then you wanted to show, you want the compiler to, or I'm sorry, the program to show you your current step of exploration. Okay. So this simple code will do that for you. Good. Now we explore around. First, we move up. So in here, to move up, remember the current row and the column cells of the frontier is in B. So to go up, that means, remember the above cell is a cell that has the same column as me, but its row is -1. If you have two cells above each other, okay? If this is the frontier, this cell here has the same column as the frontier as this one, but its row is equal to the row of the frontier -1. So what I'm saying here is that if B of row -1 larger than or equal to 0, I mean if this is in the map, okay? If it's negative, then it's outside the map. And it's not visited before, means its entry in the visited is false, then this is a valid node to explore. So let's explore it. Explore it means put it in the queue. Any entry in the queue needs 4 values. Needs a row, a column, ID, distance from the start. Good. So we're here adding to the queue this new node. Its row, it is the same row of the current frontier minus 1 because it's above the frontier. But it has the same column. The idea I'm calculating here using that equation, row plus column multiplied by the row size. But remember here the row is the same row of the frontier minus 1. And the distance, for example, is the distance of the parent, the current frontier plus 1. So for example, if I'm currently the starting node, so basically my neighbor cell is just congested to me, or just my direct neighbor have is one cell away from me, and the distance of the start is 0, so 0 plus 1 is 1. So you just need to add 1 to the distance from the start of the frontier node. In this example, in the first iteration, it will be the start. So 0 plus 1 is 1. Then in the array called, or I'm sorry, in the dictionary called parent, remember this is a dictionary, okay? In the key called ID, in the current cell, put the ID of the parent, which is the current frontier. The current frontier, again, node is in B. This is the head of the FIFO. Good. And we mark it as visited. We visit this parent, so we mark it as visited. So future frontiers cannot visit that again. If you need to show the grid, the current exploration step, okay, then you need to put this in true. Then it will show the grid for you, okay, using this function called the show map. So show map is actually a function that takes the grid as input, and there it will just make a tool. Let's see it. So let's explore it. So this is show map. Let us see where. Yeah, it's in here. So it's very easy one. So it takes the input map or the grid as input. Then you will have here two a nested loop. Okay, one index is running through the rows, the other is running through the columns, which is J, and in each time we see out or we show the value of this input map, the value of this cell. Okay. After moving up, we move right. And we do exactly the same, except that the node on my right is actually have the same row, but its column is my column plus 1. The column of the frontier plus 1. But the distance is again the distance of the frontier plus 1. And the ID can be calculated using the same equation, although now, since the current node that we're exploring has the same row, so here is B row, but it has column plus 1 as a column, so this is column plus 1. Then we can determine again the ID. Here we are setting its parent in the parent dictionary. We mark it as visited, and we're gonna show some output, if you like. Then we explore left, then we explore down. Each time we do the same. After exploring the 4 parents, we are done with this node. Okay? We already popped out this node in the beginning here. Just reminding you. We don't need actually to wait until the end of the 4 checkings. We can do just from the beginning. Then we change its notation from F, which is current frontier, to E, which means an already explored frontier. Okay, and we show the grid. Okay, and we're gonna continue in that until we find the goal, or we just explore everything in the queue become empty. Okay, so this is the breadth first search. If we didn't find the goal, I mean this condition here hasn't satisfied because there is no route basically between the start and the goal, we will find ourselves exiting the loop because of that condition here, because the queue is empty. And in that case, we're gonna return -1. So -1 will mean to us in the future that there is no route between the source and the destination or the goal. Okay, let's go back to our main function again. So here is we are doing the breadth first search. And here is the variable that will show us if we discover a route or not. If this variable is not -1, then there is a route. If it's a -1, then there is no route. Okay, if there is a route, if this guy is larger than 0, then construct this route. Show this route to us. And this is what we are doing in here. Okay. We basically search the parent of any node, okay, and go back until we reach the goal node. Okay. So we are saying that while parent of node doesn't equal to start node, okay. So I get here the parent. Yeah, there's some things that I forgot. So here is I'm defining a variable called the parent node, okay, which is equal to parent of. Remember, parent is a dictionary that has for each cell the parent of that cell. So in that node here, we're gonna bring back or calculate or get the parent of the goal node, and store that value in parent node. Here is how to convert back from rows and columns into ID. So we take both equations now. The equation that gives you the ID based on the column and the row. And here are the equations that do the opposite. Based on, if you know the ID, how to get the column and row out of that ID. Then we define 2 other variables called row parent and column parent. Okay. So we go to this loop here, and this loop we will exit it if we reach the start node. So I put here the condition while parent node doesn't equal to the start node, just to keep looping. If they become equal, if you discover the start node as a parent of some node you have, then you just reached the the start node. So no need to, do more looping, basically, because the start node has no parent. This is the first node that we have explored. So we need to exit. So this is the condition of the exiting. So if you remember, guys, I write the path as a chain. Goal, then its parent, then the parent of its parent, and so on until I reach the goal. So here I put the shortest path is G, then I put, the notation here, which means, the parent is whatever comes next. I'm sorry, whatever comes first, which is the parent. So it will print G in the beginning. In the first loop, it will print the parent of the goal and that guy. Then it will go, until it reaches the start. And now here is the tricky part. How to set, the directions inside the map using these, neat symbols. V, the exponent, greater than and less than. Okay. So basically, if the row of my parent is less than my row, or if, the subtraction of them is -1, that means my parent is is above me, we can say, or down me. Down, yes, down. So I need to go down to it. If my parent is above me, I need to go up. If it's on the right, I need to go in that way. Left, I need to go in that way. Obvious? Then we switch. The current node will be the parent, okay? And then we basically do the same with it. So we start with the goal, we find its parent, which in our example was node 7. Then we take 7. Now this is our current node. And we find its parent, which is 11. Okay, then we take 11, find its parent, which is 10, and so on and so forth until we reach the goal. It's a start node. Okay, and finally we bring to the start here. And we show the map after putting that neat features of these arrows so that we can know the start, the way or the shortest path from the start to the goal node. Okay. Any part of the code was not clear? I know it's a lot of coding, but just let me know. Is any part was not clear, guys?
I had a question. What's a verbose input?
What is what?
Verbose, and I forgot what the name was called.
In what part? In what? Do you remember what?
Just go. I don't remember. Oh, right there. You can stop right there.
Yeah. Verbo. Okay.
Yeah.
Verbose is, if you talk a lot like me, this is verbose, right?
Oh, I know, but what does that signify in the code?
Yeah. So what I'm saying in here, okay, if you wanna verbose output, a more informative output for you for debugging, for example, okay, then do whatever. So here, what I'm doing exactly, this in here. So whenever I discover the node, okay.
No, I'm talking about like the value verbose output has. Is that just a true or false value, or?
Yeah, if it's a true or false.
Oh, okay.
If you want to show outputs, okay.
Yeah, that's what I wanted to know. Yeah.
Yeah. Any other questions, guys? So give it a read, okay? I will continue with you right now, exploring more examples, okay? But you should read it carefully today, for example, because I will publish the homework today. I almost finished it. Then you're gonna do the depth first search. So read the code again by yourself, watch the video. It's published maybe after a few hours. If you didn't, if there is something not clear, I can explain tomorrow again the part of the code that is not clear for you. Okay, so please do that today. But let's continue with more examples. Okay, so we have verbose output. Okay, so let's make a breakpoint. Yes. Any question? Yes. No question? Don't be shy. Okay. So we're gonna verbose, make a verbose with break. So when I have verbose output, I will show each exploration step. And when I have a breakpoint, means this is true, I will stop after each step. Then I must hit the keyboard to continue to the other step. Okay. I will choose some example. Let's choose this example 5. Okay, for example, example 5. So we're gonna just write 5 here. That's it. Okay, if we save, this guy will be not highlighted and this guy will be highlighted. And we're gonna decrease a little bit the, let's do it 100 millisecond. This has no value now since you make a breakpoint or make a break after each output, but let's do it. Let's make it short. So let's do that and let's see what's happening. So this is the first step, the map after the first step. So my first frontier is a starting node. Okay. So here that means the starting node has discovered this node here, has explored this node. So it's asterisk. Asterisk means, or the this multiplication sign means it's an explored node or discovered node, but not yet frontier. Okay, and here is our notations again. S is a start node, D the goal node. Where is the goal node? There is the goal node. So let me change this D very quick. It should be very easy. Yeah. So let's do it in that way. Now it's crystal clear. Okay. So G is the goal node, which in here, just above the start node. 1 means obstacle. So these are obstacles, basically. Here's another 4 obstacles. Okay. 0 means free and unexplored node. Asterisk means discovered node. F means current frontier. E means previously explored frontier. The only node that I will not mark as a frontier is a start node because it's obvious that, or clear that the first node is always, our first frontier is always the start node. Okay. So in our first step, we discovered that node above us. Then we go right. So let's do that. Yes, right. You see? Then left. You see? Then down. Good. Then we finished that one. We finished the start node. Okay? And we need a new node, a new frontier right now. We have actually 4 now that we can choose from them. We go with, up, right, left, down. So we go up first. So this is our current frontier now. Our current, yes.
You know where you have the little asterisks? That's equivalent to the blue cells in MATLAB, right?
Yes, that's right. Yes. The asterisk is right, is actually the blue cells. And the F here means is the red cell. Okay.
Well, after this, do you think you can show me that line of code that shows the discovered nodes?
Okay, it's in here. So in our function here, the breadth first search function, which is that one here, okay? When we take a frontier, here is a frontier. So this is B is the current frontier. Okay?
Mm-hmm.
So B is the current frontier. And we're gonna explore around. So we move up. Move up, what's meaning by moving up? Moving up explores the cell just above me. The cell above me, or above the frontier, has the same column, but its row is row of the frontier minus 1. Okay, so look at here. So this is the row of the frontier minus 1, then this is the guy above me.
Right.
And here I am saying if it's inside the map, then do whatever. If it's outside, then it will not, this part will not be executed at all. Okay? So this is the part that shows that. So it's first play with the grid. Okay, and this is actually a copy of the grid. It's not the actual one. I just copied it in that variable. Okay, if it's not the goal, because I don't want to mess with the symbol of the goal. Any other cell I can do that. So both here asterisk means we explored it. Clear?
So as long as it's not the goal, it'll explore the ones around it, and
If it's a goal, it will be explored also, but I will not show the asterisk in the output.
Mm-hmm.
Okay, so but I will, of course, I will explore it to add it in the queue. Then I will pick it from the queue. Then oh, this is a goal. Then we break the loop.
Right.
Okay, but to show the asterisks are only shown for the any node except the goal node. Okay, but of course the goal will be explored as well. Clear? Clear, Johnny?
Yeah, it's just the potential nodes that can be explored, right? As long as it's not like obstacles or something.
Yes,
right?
That's right. Yeah. So this current frontier right now has this cell, which is of course a visited cell before, but it has 3 neighbors. These 3 zeros will be explored. We explore above first, the above node, look, then the right one, then the left one. Then it's finished. It's done. We are done with it. So I will make it E. Means it's a previously explored frontier. Okay, that's it. Just to show you which was a frontier node before. Okay, good. Now we're gonna choose a frontier now between these asterisks. Okay, so let's keep going. We're gonna we took the up one, then we go to the right. Okay, we're gonna explore in the right. The above one is already explored. The left one is already explored. So the next step will be the down, my below cell. Then I am done with it. Then pick another frontier. This guy has only one cell to explore, which is the cell below. Done with it. Then the below cell will be below the start will be the frontier. This has only also one cell to explore, the below one. Then we are done with it, and so on. This is basically the map that I was discussing with you in our lectures with MATLAB. Okay. And after maybe, I think 29 steps or 29 clicks here on the keyboard, we're gonna reach our goal. Yes, actually we reached it right now. But since the goal is, first in, first out, it still has, there are still some nodes in the queue that should be explored first. But once we pick the goal, we can construct the path very easy like this. So to move from the start to the goal, we just go up. Right? Clear or not? Maybe the coding is a little bit, I may confuse you while exploring the code with you, but really, you really need to read it by yourself. Okay, and you need to do that today, because tomorrow I will do some other stuff. I will go back to MATLAB. Okay, you guys will do the depth first search and Dijkstra and A star all by yourself. You will just have this code, a complete code with the shortest path and everything, okay? And you need to modify in certain parts that I will show you in each assignment to implement the depth first search, Dijkstra and A star. Okay, and this is very important because in the real world, when you code one of these coding in a real robot, usually you will do it with C or C++. Okay, there is no MATLAB there. So you will do it with using C or C++. So you need to know or to understand well the C++ coding. Okay, this code, by the way, just to for some ethical stuff, this code, by the way, I got it from some GitHub web page. I will show it later. Okay, but I make a lot of modifications in order to make it more clear for you. I wrote a lot of comments. I make a lot of changes. Okay, the debugging stuff, the examples, many stuff. Okay, but the main structure of the code, the breadth first search itself, it's actually not my code. Okay, but it's available for anyone to use, I would say. Good. So let's do another example. This might be the, yeah, let's do example 2. It's a little bit bigger. This is the last, not the last, the one before the last. Okay. Let's do that example. And let's, remove the breakpoints and just keep the delay. So there will be some delay between two outputs. 1 second exactly. So let's see. So you see, guys, how it will evolve, okay? It may take 1 minute or something, or 1.5 minutes. But you see how it's evolving, how it's exploring, okay? If something not clear, if you have some doubt about any step, I can stop that, by the way. It's easy, okay? So I can step, for example, if you are, I can do the, now it's stopped. I can debug with you, whatever. So let me know if there is something not clear. It's exactly the MATLAB GUI stuff, but in a more handmade way, okay? Of course, there is no red or blue. Yes?
Can you show me the code that, like, let's say right there, you see where F is? You know how it explores the bottom one?
This one here?
Bottom asterisk?
This one?
Yes. You know how there was an asterisk to the right of it, I believe, but then it checked the bottom one. How does it know that there was an asterisk before that?
So, okay, so this is, I will show you step by step exactly. So this is before any exploration. You are asking about this, the asterisk in here. Okay, this is the one that you are asking for. So let us see how this asterisk become asterisk in the first place. So, okay, so we let's assume we are stopping here now at that step, at that all. So this is the current situation of the map. Okay. Now, if you look at this map, there is no F's. We have only S's or E's or asterisks. There is no F. Okay. So we need a frontier to explore. So these are the nodes that are not that are explored in the previous steps, okay, they are in the queue, but they are not chosen yet to be a frontier. So we're gonna choose one of these asterisks, either this guy or this guy or this guy or this guy or this guy. Okay.
It'll be the one that's after the explored, right? The previous explored one in the queue.
So it's based on the order those guys were explored. But looks like this one here that I'm marking right now where was explored first before these asterisks. So that in the next step, which is this one, it is the one that is chosen to be the frontier, you see?
Right.
Then this is our now current frontier. We didn't look at we didn't answer the question yet. So this one now has to explore around. So this one is explored or visited before. So if we check the visited, there is a record visited. If we check the value, it will be 1 or true. That means it was explored or visited. If the frontier checks that one, it will be also visited. But this one, it will be 0, 0, or false. So that means it's not visited yet. So we're gonna visit it, okay? And since it's visited, we're gonna add it to the queue and we mark it in the map with asterisk. Now this is the answer of your question.
Right.
Okay, and that's it.
Right. I wanted to see like the code that checks like if there's already an asterisk there or
no, it's not a checking if there is asterisk there or not. It's a checking if it's visited or not. So look at here. Look at where? Yeah, no. It's basically, yes. So in here, look. So we are checking the down one or the bottom node, okay? So here we are checking if the cell in the bottom is it checked or not. So if visited or not. So if the location of that cell is true, then it was visited before, and we don't need to visit it again.
I see.
Okay, we don't check the asterisks. We make it using the visited array. Okay. Clear?
Yes. Thank you.
Okay, let's continue. But I can't, make it quicker once it starts. So let's stop that. Okay, it will take time. So let's do it with, a much quicker, with a smaller periods. So let's make it, for example, 500 milliseconds. So let's do that. And then, guys, if there is a step that you are not sure about, just let me know. I can stop this.
Dr. Abdulrahim?
Yes.
Quick question. So this assignment, it's just building the shortest path again, as in previous assignments, or is it more expanded?
No, so in that assignment specific, you're gonna do everything. So I will give you the main structure, okay, which basically is the breadth first search. But I will, you know, highlight some parts that you're gonna continue or you're gonna build from scratch, basically.
Okay.
Okay. So, for example, for depth first search, for example, we here using FIFO, okay, or this queue. But in depth first search, we're gonna use stack. So you can search on the internet, you know, how to build stack in C++, and it's very easy, very easy. Okay, you're gonna just change one line of code, and that's it.
Okay, and for the visual, do you want that as a separate class or object in the program, like a different C file that the main file calls to, or do you want it as part of the main file?
No, you will have every. Okay, so you will have the main structure. The part of the main structure is these examples. Okay, you just need to, you know, based on your preference, you need to make some variables true or false to show that you know, that output here that we are currently viewing. Okay, so you see, guys, it's finished. I'm sorry, just, you know, explain this very quick. So here is the path. Okay, we go right, then we go down, then we go right again, then we go down again until we reach the goal. Okay, so in the assignment, everything will be implemented. So I will highlight, including the visual stuff. I will just highlight some parts, few parts that you're gonna do from scratch. Okay, most of them are just 1 or 2 lines of code.
Okay, got it. Thank you.
So let's do the last example, which is example 8, which is, you know, as usual, has no route. So this is example 8 here. You see, guys, so we have here, you know, a wall from wall to wall. Okay, from this end to this end. And the goal happens to be above the wall, and the start happens to be down the wall or below the wall. So there is no route between both. So if we run this, we of course will explore all the nodes below this wall, this end-to-end wall. And at some time, you will find that the code will find that the queue is empty while we didn't discover the goal yet. So it will just return -1, and -1 means to us, or means in the code, that there is no route. And it will give you a hint about that at the end. Yeah. So look at here. So this is the wall here, order ones, and here is the cells that are explored. So all the cells below the wall are explored, of course, except the walls, of course. So all of them were a frontier, and they explored the frontier, and, you know, there is no value, there is no route to reach the goal, which is above the wall. So it just returns -1, and, you know, copies this message for you that there is no route from the search to the destination. And again, let's change this D to G, okay, to make it more clear for you, or less confusing, we can say. Yeah. Okay. So you will have, for example, so for depth first search, okay, you will not use a queue anymore. Queue means FIFO. Okay, so this line here should be changed to stack. So you just search on the internet how to implement stack or stack structure or LIFO or FILO structure in first in last out in C++, and you will find that you will just need to change only one line. So this line will be removed, and you just include another line, maybe with the same length. Okay, basically that thing here will be changed, just to keep the queue as it is, the name, the same name. But here it's a queue. In your depth first search, it will be a stack. Okay, or you can change whatever, you know, that's fine. You can also change the name. It's up to you. Okay. but please keep it. It will be much easier even for me when I mark it. And by the way, by the end of this week, you will have all the assignments marked. Okay, because today is a census day, and you know everybody has decided to continue or not. So now we can mark without having the risk of marking someone that is not in the course. Okay, so yeah, that's it for the C++ coding or for breadth first search, and see you tomorrow. But by the way, so just two announcement very quick. You guys saw my announcement regarding the kits delivery. Okay, till this I asked you to send me the car model, you know, color, you know, some specs about your car that you will come in, so that we can verify easily who are you. Beside, of course, is your ID card. Okay, but this will make it easier for us. So please, only two of you or three of you have sent me their car models and, you know, color. Please, the rest of you should do also should do the same as well. Please do that as soon as possible. For tomorrow's lecture, I'm sorry, for maybe 10% or 20%, we may not be able to take it. Okay, because I have some urgency, just like Saturday, and I'm very sorry for this. Okay, this will not happen again. I promise you for that. So maybe I will of course announce this. Okay, but maybe the lecture will be cancelled. Okay, but I will let you know. But this is, I think it will be a low probability, maybe 20% or something. So just, you know, keep tuned. I will send you if I decided to cancel it. Okay, and that's it. Okay, if you have any question, please you know, email me or something, and please read this code today. And if you have a question, and if we take the lecture tomorrow or on Thursday, let me know to revise again or review again with you the coding. Okay?
Professor?
Yes.
Do you know how long it's going to take for them to ship the robotics kit to the people outside of Bakersfield?
So on the same day or the day following, we're gonna ship them. I don't know, there is a shipping department in the, I don't know, and we're gonna just give them the kits and they do the rest. I really don't know what kind of shipping they will do, what kind of companies they will, you know, use.
So we don't know when. So you're gonna ship that day of, but we don't know when it's gonna arrive.
It should be shipped to you or mailed to you.
Yeah.
On Monday, September 28th, or Tuesday, September 29th.
Oh, so it'll arrive.
I don't know. And I understand.
Okay.
I understand.
Oh, okay. All right. So we pretty much don't know then.
Yeah, but we will not use them. We will not use like, we still have three very important topics. Okay. During these 2 weeks, or maybe they will take 3 weeks. I really don't know.
Oh, okay.
We have something called artificial potential field. Okay. So it's another way to build a route between the source and the destination or the goal. And this one is really, you know, it's easy to program, but it's not that, you know, easy to understand. It's not like those guys. So this may take time with us, maybe 2 or 3 lectures, although it's just one algorithm.
Okay.
Then we have something called probabilistic roadmaps and random search trees. Okay, this is another 2 topics that we're gonna also take time, maybe 3 lectures or 4 lectures. So for these 2 weeks, we're gonna not, you know, we'll not, you know, go to the. But after these 3 topics, we will go to the kit.
Okay.
And we'll have very enough time with it, so don't worry.
All right. Thank you.
Any other question? Okay. So
yeah, quick question.
Yes.
So for this code, is it also calculating the step or no?
Oh, I forgot to do that. It's not calculating the step. Okay, you can add this. This is very easy. So you can add counter here. You can add a counter here. And this is good for you for debugging. because you know for A star, for example, this number should be less than or dexterous or maybe comparable to Brett's first session. So it will give you a good
Reference.
yes, if your coding is working or not. So you can add this counter. Let's say we can do that very quick right now. So we can do, for example, int counter equal to 0. But this counter should be incremented with each node or neighbor you discover. So in here. So let's call this step counter. Okay. So step counter here, plus plus. Okay, and you just add this for all other neighbors that you discover. Okay, that way you know how many steps you have, and you can also show it. So you can put here, for example, see out end line just to go one line.
Yeah.
Then current exploration step equal to, and put this guy here. Oh, yeah, it's fine. Step counter and the end line again. So you know for each step what's the number of steps that we have done. So why we have end line, not just end. So it should be end line. Yeah. Okay, now we will have, let's do that very quick. If we can, it's not shown or shown. Yeah, for some reason it's not shown, so we have a problem.
It shows at certain times.
Yeah,
You
it
can
shows
see.
somewhere.
Yeah, but wouldn't you have to move that to where you're displaying like your whole notifications and stuff?
Oh, we can do, you mean in the show map, right?
No, you're
Outside, outside, maybe outside here. Okay.
Can't you put it on the end of your main?
yeah.
No, because, okay, this is basically not the main function. Okay, we are reading the function that called from the main function. This is one thing. The other thing is that it's a local variable inside this.
Right, but if you made it global, then it'll work, right?
Of course. Yes. We can do that as well. Yeah, so it's just one variable, so it's safe to do that. That's not so okay. So let's do that. So int step counter equal to 0. Okay, and let's change. Yes, let's change that here. Okay, and step counter. Now we need only to show it. So we need to show it at each neighbor we discover. So we have 4 neighbors to, yes. And I think now it should work. Let's see. Yes, it's working. But let's do a little more trick to make it more visible on a separate line. You see, guys? Yeah, but one of them, not one of them, all of them needs this. So we're gonna add this little trick in the other 3 as well. Yeah, now it will be crystal clear. Look. It's only not shown when I change the F to E, so don't worry about that. But whenever we discover a new node, we show the step at which it was discovered. The number of steps here was high, I remember. We're gonna see now. Okay, let's check how many steps. Oh, it's not again. Yeah. Here, by the way, guys, we are, having a new frontiers, but all the cells around are explored, so that it's not shown. But somehow, some steps above this. Yes. So at this point here, yes, that was the number. It was 21. After that, all the frontiers that were discovered or explore will have, all the neighbors will be are visited. Were visited. So we will not, make other new explorations because basically they were explored before. Okay. So the counter just stopped at 21. Because new frontiers will not find any new cells to discover or explore. You got that, or it's vague for you?
Nope, got it.
Got it.
Good. Okay. Any other question?
Nope.
Okay. So have a good day. See you tomorrow.
You too,
Bye-bye.
Professor.
Thank you.
Yeah,
Yeah.
It's not for this, but it's for like the homework for the A star. I just wanted to see like the GUI map that you made for an example one.
What happened?
No, I'm just saying, like I want to see the result you got for your map.
In the MATLAB, right?
Yeah.
Okay, let me check.
For the A star.
Yeah, okay. This is the main and A star, right? You want example one, this guy, right?
Yeah, correct.
Yeah, what is the problem with yours?
Okay. I need to fix something.
Okay.
Yeah,
Professor, can I
but
see example 3?
yeah, but
What?
that's cool. Thank you.
Okay. What? Another question? Gusta, you have a question?
Yeah, can I see example 3? Because my example 3, it looked a little weird, but I did it on paper and it seemed right, but I just want to confirm it.
Okay. This one.
Okay, that's what it did. Just making sure.
Okay, it's right.
Yeah, it's right. I just was wondering why it was going up, and I did it on paper, and it confirmed it, but I know why now.
Okay. But you can watch the video of the lecture. You will find,
Right.
because I ran those,
I didn't see it there. I didn't see the examples there.
in the video. Because, I didn't publish the video. Yeah, because, why I didn't publish the video? Because it has the answers for the homework.
Okay, I gotcha.
Right? Okay, that's fine.
All right. Thank you,
I
Professor.
think the deadline was tomorrow, right? I will
Yeah.
publish.
Yeah, I believe so.
By the way, there is no late for that one. So there is no late for it. You either submit it, okay, or there is no late. So I think the deadline is tomorrow, and there is no excuses. So after the deadline, I will just publish the homework for it. Publish the video of it. The one that has all these examples and the code, of course. So you can check by yourself. Okay. Any other questions? Okay, have a good day. See you tomorrow. Bye bye.